We've been, except for Thursday's lecture on Helmholtz resonators, we've been talking about radiation of sound. And we did the line, the uniform line source, and now we want to do a well-known solution. It's not simple, okay, but it's used a lot. And it's a piston like this, a circular piston vibrating like this in an infinite baffle. Rigid, it's a rigid plane. And we'll start to see today why the rigid plane is there. We won't fully see why the rigid plane is there until actually I think the end of the calculation. That's where it's appropriate. And it's basically because it makes it, what happens is it's mathematically solvable. That piston, that baffle allows you to analytically solve for this case. It's an important case. People apply it to everything, okay? Even when there's not a baffle, it's because this is analytical. And once you get, once you go beyond this, problems like this are very hard to solve analytically. It's hard or impossible. Okay, so here's the geometry. This is from the book, as you can see. We've got this piston that's vibrating with peak velocity U naught, capital U naught. We have an axis of symmetry here, which we always call the z-axis. Okay, so here's our piston. We're going to call this a z-axis, and our radiation field has to be symmetric about the z-axis, right? We have rotational symmetry here. Now, there are 3 length scales here, and it makes this complicated. There's the radius of the piston, there's the wavelength, and then there's the distance you are. Okay, it's going to make it complicated, and we'll be introduced here to something new that we did not see before, and it's basically due to these 3 length scales. We're not going to make, for the time being, we're not going to make any assumptions. Okay, we're not going to assume the far field. You'll see why. And of course, the wavelength is not necessarily large compared to the piston. When the wavelength is large compared to the piston, we know what the answer is. It's going to radiate as a small source. It'll be isotropic distribution in the hemisphere, you know, on the side of the rigid plane. So it'll radiate as a small source. So we know that that has to happen, but we're not going to make any assumptions about that. We want to be able to take this down to wavelengths comparable to the size and even substantially smaller than the radius here. Why is the baffle there? Well, as I told you, we're not going to, we can't really appreciate that until we get to the end of the calculation. So I'm pretty sure it's in the notes, but it'll be at the end, and that's tomorrow. We can't finish this in one lecture, this problem. But basically it's there because you can analytically solve it. We can find the radiation field analytically. There's another reason. And we'll do a demonstration of this tomorrow. It's appropriate to do the demonstration tomorrow. And I'll remind you about this. But suppose you have a piston here, just a flat, a circular disc going like this, oscillating up and down, generating sound. Well, it's going to generate sound in this direction too, right? And in fact, what's going to happen if the wavelength gets significantly larger than the piston? What's going to happen? What's going to happen to the radiation field? We actually talked a little bit about this before, but I didn't expect it to stick anyway. So. Well, when you're sending out a compression here, you're creating a compression when it's going like that. And that compression is going to propagate outward as a wave. What's simultaneously happening down here? It's an expansion or a rarefaction. That also propagates out, right? What happens when the wavelength is large compared to the source? You get extreme diffraction. The wave bends right around the obstacles, right? So they're going to tend to cancel. This is what we call a dipole source. It has an inherently weak radiation field. Only for very small wavelengths do you get a strong radiation field here. And it's outside of our theory. Our theory is only for monopoles. It's only when you have a volume change, right? What's the volume change here? It's 0, so what's the source strength? What's the volume velocity? Remember, that's the rate of change of volume is all built into our theory. Our theory gives 0 radiation field here. Now, it's of course not right, but it's an approximation, unless the wavelength is very small. So the baffle here also serves the purpose of turning this into a monopole source. So now what we see here, instead of this disk here, oscillating like this as a dipole where there's a tendency of the sound fields here to cancel. When we go to this, now you can imagine this letting these boundaries go to infinity here. Now you see that we have a volume velocity. We have a change in volume. We have a monopole source. That's the other reason. And we'll see a dramatic demonstration of this tomorrow. And in fact, in this course, so dipole radiators are inherently weak. And in this course, we're not going to consider any dipole radiators. There's one exception, and that's the simple 2-point source. In a homework problem, we considered the 2 sources out of phase. So that's a dipole source. You can think of this source as 2 spherical wave sources. As one is expanding, its volume is increasing. What's this one doing? It's decreasing. The net volume change is 0. Okay? This is not a monopole source, dipole source. That's the only dipole source we're going to consider in this class. And we already did it in chapter 6. So, in fact, this is actually the main reason. Well, I don't know. This is really the main reason why loudspeakers are in enclosures, is to turn them into a monopole, turn the source into a monopole source. If you just take a raw loudspeaker, not in a cabinet or an enclosure, you've got a dipole source. And we'll see a demonstration of that tomorrow. These cabinets also, of course, support the loudspeaker and protect it. They're there for that reason, too. But acoustically, the reason is to turn that dipole into a monopole. Okay, so how do we solve for this? How do we set this up, this problem here? Well, the entire source is not necessarily a small source, but if I look at a little element of area there that's moving, that is a simple source or a small source. So I know that there's going to be an isotropic radiation field due to that source. And we have formulas that can handle that. So that little source will be some distance r prime, and we're going to have to integrate over all these sources. All right? Now remember here, r and theta denote the field point where where we're observing the sound field. Okay? So they're fixed in this integration over all the sources. But we'll need to integrate over the distance to sources from the center, sigma, and we'll need to integrate with respect to angle there. We'll call that angle phi later. So for a simple source, if you look back for a simple baffled source, the pressure field, forget the integral right now, falls off inversely as the distance, and there's the wave factor here. And here's here it is in terms of the velocity amplitude of the surface. So you can look, this is one of the formulas we established earlier in this chapter. We integrate over all of those sources. So this is an integral over all these elemental sources. Each of them has area ds. And it's a distance r prime from to the field point. Now, here's what we're going to, this is a serious problem. We're going to get a lot of mileage out of this. So we're going to look at 2 cases here. And you'll see why when of course we want to look at the far field. This is the overwhelming application of this, of most sources. But before we do that, we want to look along the axis, along the z-axis. So that corresponds to theta equals 0 here. Theta equals 0. And we want to do it for any value of r. We're not going to make the assumption of a far field, and you'll see there are several reasons why we're doing that, and you'll see why when we do it. We'll be able to do this today. We'll just be able to just start this. Okay. So, oops. So we call this the axial pressure. It's the pressure on the axis. Here's our piston. Imagine that the piston is here, going like this. This is the z-axis up here. We're at some arbitrary point on the z-axis. And now, because we're on the axis of symmetry, you imagine we have an element here. But all elements that are the same distance from the center. Well, maybe I need a diagram here. Here's our piston face coming like this, right? And the z-axis is out here. It's going like that. We're on the axis here. We're looking on the axis. Okay? And if I look at a source here, okay, all the sources on in this little ring right here, all the sources there are the same distance to the field point here. So in this case, because of the symmetry, we're going to take this to be our element. We're going to take this right here to be our element. We can use this formula immediately, but now it's convenient. Where is it? Right here. Now, because on that ring there, that's not very symmetric, is our prime values are the same. So we might as well just go ahead and do the first integration. Essentially, that's what we're doing. Take ds to be that area between the dashed lines there. So here we have it. ds is the circumference times d sigma. And we simply substitute that into our formula. And now we have to integrate over sigma. We've essentially done one integration here. Now, this looks complicated, but most of you are already seeing that it's not, right? You know how to integrate an exponential. It's just an exponential. And you can see here that by the chain rule, when you differentiate this, you're going to pick up, of course, the exponential. And then, by the chain rule, you're also going to pick up, you need to differentiate this, right, with respect to sigma. And that's going to give you, it's going to give you that. So the rest is just constants, things that are constant with respect to the integration. So we can actually do this integral exactly. That's very convenient. So here it is. And you can verify this if you, and you need this too, right? By the chain rule, you differentiate the exponential, you get it back. Then you've got to differentiate this. That's going to give you this. And then don't forget, you've got to differentiate the radical with respect to sigma. That's going to give you something proportional to this. So it works. And you can verify that this does it exactly. The derivative of this with respect to sigma is equal to the integrand here. Is equal to this. So we simply evaluate it at the limits. And we get this. And now, I'm going to edit this a little bit. Now it's convenient to use an identity here. And the reason it's convenient, this is simple, but you may have never seen it before. I don't think I had. We can rewrite this expression right here. And the reason we're doing it is we want to get the pressure amplitude, right? The pressure amplitude is going to be the modulus or magnitude of this. And I've got a little bit, this is easy. The magnitude of this is just 1. But what's the magnitude of that? Well, it's not obvious. So we're going to use this identity, and I proved it for you right here. You just, it's not real obvious, but you can factor out this half angle here. And this is going to be 2i times the sine of the half angle. So and the reason we do that is, now that when we take the modulus, this is just going to go away, and we're left with this sign here. So we get to this expression for the exact pressure amplitude on the z-axis. It's the exact axial pressure. It's not real simple. We're going to investigate it now. And there's a lot of brackets here, and so I think I got it right. But that's what it is, and it's exact. So, how do we appreciate this? Well, the first thing is pretty obvious, right? Far away. We know that it's got to get simple far away. All right? So, so here we are. What we've been calling the far field limit is where your field point, you have a source, and you're observing the source. In other words, the field point is very far compared to the size of the source. That's what we mean by the far field, right? So this is going to be a small quantity. The square root of 1 plus a small quantity is 1 plus 1/2 that quantity. That's a Taylor expansion or a binomial expansion, same thing. We make that approximation. The ones cancel here, okay, and we end up with this. And now look at this. This is not simple. A over R is small, right? But what's this factor? The answer is anything. It can be any positive number. Ka. What this is a comparison of the size of the source to the wavelength. And Ka can be anything. We don't want to restrict Ka. In particular, Ka can be large. So we have a small number times a large number. You can get anything here. So we're forced to recognize something here. That if we want to go far away where we get a simple sound field, right, which often happens in practice, is it's not just going to, we can't just take R to be much larger than A, the size of the source. We also have to assume that we have to assume that R is sufficiently big that it beats out this. Is that, how do I say this? Just taking R much greater than A may not be enough. We want to be able to kill the sign to come up with a simple pressure field that's falling off inversely with the distance, right? So to do that, we have to have this entire quantity be small, not just that be small. So the condition here it is. For the entire argument here to be small, we have to have this, okay? So this is important, and it comes up in all sources. It's not restricted just to this case. We're going to discuss it later. But for right now, let's not get lost here. Let's make the assumption that this quantity here is small, okay? And then what we get, the sign of a small quantity is just that quantity in radians. Some of you are still making this mistake on quizzes. Okay, you've got to be very careful between degrees and radians, right? So look at your graded quizzes. I think it came up, I've been grading so much. In a recent quiz, it came up. Okay, I don't know if it's the one that you can look at that just came available or a week ago. I've lost track. Okay, so what we get is, we just eliminate the sign here, and we get this. Now, we can check this solution. Remember how we would check this? What are we doing here? We've got this piston. We're far away. We're really far away. We're sufficiently far away that the pressure field's falling off as 1 over R. So we know what the sound field has to be. This will be behaving as a small source. And the reason is, all the elements are going to be in phase here. When I'm off at an angle here, or when I'm close to it like this, different sources are different distances. You get a tendency for destructive interference. But when you're far away, sufficiently far away, everything's going to be in phase. This has to conform to our general theory for the pressure field of a small baffled source. So does it? That's an interesting question. We did the same thing with the line source. This is a check on the solution. Well, the answer, of course, is yes, or there would have been a mistake, right? So, but here's our general expression. You may recall it's in that list of formulas for a small source. And it's in terms, of course, the relevant amplitude, which is the source strength, Q. What's our source strength here? Well, we got this piston of moving area pi a squared, and its peak velocity is u naught. So that's going to be the source strength, the peak volume velocity. So if we take, we're going to take our result here and get rid of u naught in terms of the source strength. That's different approaches here. That's what I did here. I eliminated u naught in favor of q, and then I do this simplification. It's not trivial, but eventually we get the same answer. So that's a check on our solution. The solution has to reduce, even though it's not necessarily a small source. If you're on the axis and you're very far away, it's going to look like a small source. Everything's in phase. Everything's in phase. Okay, so now let's go back now and let's look at this issue of what's going on here. In this case. So here's the exact pressure amplitude. I've rewritten it here. Now, what's going to happen as you start, when you're very far away, when you start from R being very far away, this is just going to look like 1 over R. Okay? As you decrease R, what's going to happen? Well, the approximation is going to break down, and now you have to contend with this. And you can see that this argument is going to vary. And what happens here is that you're going to hit points here where this whole everything inside the curly brackets here is a multiple of pi over 2. Pi over 2, 3 pi over 2, 5 pi over 2. That's going to give you a maximum. So this is a constant. So the pressure field, as you move down, you start way off here. It's falling off as 1 over R. When you get inside here, you're going to hit maximums. They all have the same value, which is curious. You're going to hit maximums with all the same amplitude. And you're also going to hit minimums. You're going to hit in between, interleaved between the half integral, pi over 2 values, pi over 2, 3 pi over 2, are going to be pi, 2 pi. You're going to get 0. So I don't think this is obvious, but on the axis of this disk right here, there are going to be points where you get exactly 0 sound field, perfect pressure nulls. It's not obvious. In fact, there's a famous story about that, kind of about it with respect to light, right? Almost everything here has a parallel to electromagnetic radiation in acoustics. And the story was like, it's 1700s or probably, I don't know. It wasn't the minimums, it was the maximums. In fact, you can get maximums here. And typical light situation, gosh, I'm getting into trouble here. That was a different situation. It was a complementary situation where you have an opaque disk. You have a light source here, a plane wave coming in, and an opaque disk. And you look at the light on the axis here. And Poisson did this. I think it was part of his PhD dissertation. He found that when you're at some distance right about here, you get this bright spot. It's now known as Poisson's spot. And when he defended his thesis, he was ridiculed by one of the professors because the professor said that's obviously an incorrect result. Well, no one knows the professor's name anymore, but it's called Poisson's spot, and it's there, and you can see it. Take a coin, and I haven't done this for a while, okay? So you might want to take a coin and put it up and block the sun, okay? And then move your eye like this. Yeah, it's been a really long time, so be careful if you do it, okay? And you can, there's a bright spot there. It's well known, okay? That's not the same problem as ours, but it's kind of a complementary problem. Here we have sound essentially emanating, from this disk. There was a light wave coming here, and the disk was, and that's an acoustic problem too. I've never seen it, but. So anyway, this is a remarkable result here. We have these constant pressure maximums and perfect destructive interference. These extremums, we can handle these together. They occur when you either have, the maximums occur when you have pi over 2, 3 pi over 2, etc. The zeros occur when you have 0 pi, when this is pi, or 2 pi. Okay, so we can lump them all together. We set the argument of the sign equal to m pi over 2, where m is a non-negative integer. So it's remarkable here that you can get complete destructive interference, I think. And furthermore, there's something else that's sort of mathematically interesting here. The next step here, the next natural step here is to solve this for R, to find the locations of these extremums, right? And you look at that and you say, oh, it's going to be a quadratic equation. You got when you clear out this R down here, and you want to square all this, it's going to be a quadratic equation. Well, it turns out to reduce to a linear equation. So I guess what's happening here, I haven't. So this is going to be R here, and this is not going to be the same. I don't want this. Maybe I better call this capital A. So you're going to get, it's going to look something like, it's going to be a quadratic equation. However, what happens is, one of these is 0. A or B is equal to 0. Okay? Sorry, I've forgotten. It's been a number of years. But you can do it. It's interesting. And it's very peculiar. This just looks like a quadratic. When you put this in standard form, you're going to get this, but it reduces to a linear equation, which is very nice. We have these nice, simple solutions here. Here's how it's KFCS write it. It's a little confusing looking, but this is one way of writing it. Here's the result. So these RMs here, and you notice to understand this, m is equal to 0 corresponds to the infinitely far away, where we're going to have a minimum, right? The pressure is falling off as 1 over r, so that's an extremum at infinity. So m equals 0. The r0 value, you can see here you're going to get infinity, right? That's the first thing to notice here. The next thing is, how many extremums do you have? Well, that depends upon the wavelength, and you know this is coming. You know that the smaller the wavelength, the more number of extremums you're going to have. It's easier to have that destructive and constructive interference. So what happens here is that you always have the m is equal to 0 solution. That's at infinity. What about m equals 1? That's the next thing to look at. Well, it may be that this value beats out that value. So what do we infer from that? If this is negative, what do we infer? It doesn't exist. This has to be positive. Okay? So that can happen. It all depends upon the wavelength relative to the radius, relative to the size of the source. So it's best here to appreciate this, and this is what KFCS do. It's best to look at a specific example to get a feeling. Let's suppose Ka is equal to 8 pi. All right? The pi there is for convenience because K is 2 pi over the wavelength. So Ka is equal to 8 pi corresponds to a wavelength that's 1/4 of the radius. So we've got this radius here, right? And we've already done this. This is, we integrated, right? So here's the radius. When you take a wavelength about this big, that's the wavelength. Okay, I'm just going to put it on here. It looks something like this. That's what we're asking. What's going to happen here along with the pressure field, or the axial pressure field? Now, when I see that, my guess is that wavelength's small compared to the radius. We're going to get a ton of extremums, okay? We're going to get a lot, I would guess. How many? I don't know. We have to analyze it. So let's do that. You can see it's fewer than I thought. We actually get 8 possibilities, okay? We always have this This is always there. The pressure is going to go to 0 to infinity. And as you come in from infinity, and that's the better way to look at this, is come in from infinity. You hit the next one here. The next thing you hit is a max. That's a min at infinity. R1 is a max. Then you hit R2, which is a 0. And then you hit R3, which is a max of the same value, curiously enough. Same pressure there, that's not obvious. And then you keep marching down, and eventually you run out of extremums, okay? If you want more extremums, decrease the wavelength. If you want less, increase the wavelength. It all depends upon the Ka number, the relationship of the wavelengths compared to the radius of the source. Now, KFCS actually make a mistake here. You can show that for Ka is precisely equal to 8 pi, it turns out that R is equal to 0 corresponds to a pressure 0, a null. It's just the way it works out for this value. So they should have had this curve here. This should not stop there. It should go all the way down to the origin. And I made a comment on that in here, just in case you want to. So they made a mistake. Everybody makes mistakes. Okay. Now, this is really sort of the main point here. We're slowly getting at the main point here. When we talk about the far field of an acoustic source, we imagine a pressure that falls off, inversely as the distance, 1 over r. And we also imagine that the pressure nulls are simple surfaces, typically cones, right? Typically cones, as we've seen. Well, we've got a problem here. For this to be in the far field here, to have the pressure fall off 1 over r, we have to be out here. This is a little bit of a problem here. We don't have to be very much greater than, this is r over a here. We don't have to be very much greater than 4 times the radius of the disk. Twice is not bad here. So KFCS, they just say, well, you got to be greater than this extremum, wherever this lies. It so happens that, well, for this case, with the wavelength being 1/4 of the radius, that this maximum here approximately corresponds to 4. It's just an approximation. It's okay. It's just a rough right now. So to have a pressure field, a far pressure field that behaves simply, which is what we would like and which often happens in practice, we have to be, beyond this value. KFCS labeled the demarcation as this. I call it, let me give you the value here. Well, let's just call it R1. So R1 is right around here somewhere. It's actually, I think, right around here. KFCS say that you just have to be beyond there to be in the far field. I think that's that's pushing it too much. On the other hand, this is saying that you have to be much greater than this value. You're going overboard. So what some people do, and I don't think this was available in math type, when people want to denote that, you can say it in words, but when they want to denote it mathematically, they'll often do something like this. This is the way that it probably should be denoted, but I couldn't find that, I think, in math type. So anyway, we've hit another condition here. Before we get to that, let me look at the notes here. Just some particular points here, particular values. When the wavelength is equal to the diameter, you can show that it's a very simple case. So we're increasing the wavelength from our example right here. From our example, we're making the wavelength bigger, right? Instead of 1/4 of a radius, we're heading towards the wavelength equaling the diameter. This is going to move down like this, and when the wavelength equals to a diameter, R1 becomes exactly equal to 0. So the sound field comes in like this. It comes in like this and rolls over and comes in with 0 slope right at R equals 0. That's mentioned here. Okay, so at that point there are KFCS say everything's in the far field. Well, that's pushing it a little bit. Okay, I think to say that this that behaves like this is behaving like that. I think that's a little too much. But it's all up to you what you want to decide. There's no fixed convention here. Okay, so what we've seen here is that we have to supplement our condition of a far field. In the past, we've said, well, you have to be far away compared to the source, the size of the source. No statement of the wavelength. And what we've found here, and it's really not surprising, that the wavelength can introduce a problem here. If the wavelength is sufficiently small, your field may not be falling off as 1 over r. And that's what we've seen. That's what we just saw. So we have an additional requirement here. We have to require that r is roughly much greater than r1, right? We have to require this. And when we write that out, here's what r1 is equal to. You can see that our new this right here does not involve the wavelength at all. It's just you're far away compared to the size of the source. But this involves both the size of the source. This condition involves both the size of the source and the wavelength. And here it is. Here's R1. Now, so we have these two conditions, right? This is the one we always think of first, right? So what you can do here to make life simpler for yourself is don't just treat these as independent. Assume that this is true and see what it implies here. You can simplify how we approach this. I'm not going to go over here. It's short. Here it is in detail. But I'm just going to give you the conclusion here. The conclusion is, as long as the wavelength is not small compared to the size of the source, you don't have to worry about that. It's going to be 1 over r. Okay, it's only for small wavelength. You can see that. It's only for small wavelength that you're going to hit this problem. And by small, we mean small compared to the size of the source. So we can summarize here. And this is true for all sources, all realistic, all non-infinite. You can have an infinite plane going like this. It's not a practical source. But for all practical sources, there are two conditions. I'm using L to denote the characteristic length of the source, the size of the source here. In this case, it's the radius or the diameter, doesn't matter. Here it's the length or the uniform line source. So this is just some characteristic length scale of the source. You have to have these two conditions, and you only have to worry about this one when the wavelength is much less than the size of the source. And this holds for any sources. KFCS don't point this out, but this is I suspect it's well known in optics, but I don't know. We will encounter this in the next experiment, which is probably next week, right? Okay. So what's going on here? I think you all probably have a rough physical field. Let me just make sure. When the wavelength is small compared to the size of the source, we have strong interference. We've seen that before in the angular distribution, right? Here we hit this additional requirement for a far field by looking on the axis here. But in general, when you have any kind of source and you're in the far field, we have this, they're all typically cones of one sort or another, simple surfaces where you have zero pressure. And the pressure falls off inversely as the distance. And when the wavelength is small, how far do you have to go to get from one pressure null to the next? Very small change in angle. That was shown in the anechoic chamber. By the way, Gene, have they edited?
On Taylor, who's editing it.
Okay. You might want to talk to him a little? Have you talked to him recently?
Since like last week, last week.
Okay, all right. So we'll make that available for everyone, right? Okay. So we know we have this source here with a relatively small wavelength, okay? Small compared to the size source. You know, and you heard it in this room too, with just a single source due to sound bounce, interference due to sound bouncing off the walls. You move a little angle and you go through, you know, you can go through several nodes. Just move your head a little bit. Okay? Well, what we've seen here is that you can have the same effect here on the axis when you're changing the distance this way, unless you're very far away. So there's a difference between the angle case and the axial case. In the angle case, you're always going to see these nodes, okay, and they're closely spaced. Here, you're going to hit nodes here, okay, unless you're sufficiently far away. And that's this condition right here. That's the condition. So it makes, you know, it makes some qualitative sense. And the smaller the wavelength, the farther away you have to be. Okay. So does anybody have any questions? We can now move on. That's the axial, that's the sound field of a baffled circular piston, rigid piston, along the axis. And you can see now why we analyzed it, why KFCS analyzed it exactly. It points out this other condition. And they should have emphasized that. They don't. But it's not just for this piston. It's a general statement. That's why I switched to the L here, to a general statement. So next what we're going to look at, and this is the practical case of the far field. And now I see I have to edit this. We have to now add this other condition. I'll put that in there. I didn't do it. So most people, you know, tend to ignore that other condition, but you need to be aware that it's there. Okay, you need to be aware. So we really have two conditions here. But the second one only comes in for when the wavelength is small compared to the size of the source. So it turns out, as I mentioned to you before, this problem can be solved exactly. Well, you know, in the far field limit, we can solve it. It takes some effort and involves some advanced applied mathematics, but it's not too bad. We'll go through that. So here's our geometry. All right, we're now going to be at any theta in the forward plane here. You know, any theta. So theta can be 0, which is the axis, all the way out to 90 degrees, where some distance r. And now we need to integrate over the elemental sources. We have a two-dimensional integral, right? So always, in physics at least, and probably engineering too, you know, when you hit a multiple integral, you want to try to, it's nice to split it up into geometrically sort of physical individual integrals. And what we're going to do here is we're going to view the sound field here as the sound field due to a collection of line sources. It's not obvious that this would be the way to go here because the symmetry is not obvious here. But there's nothing that stops us from doing it, and it will lead to the solution, as you'll see. So here's our disk, right? Let's look head on here. Here's the disk. And what we're going to do is, I'm going to consider a thin line source right here. This thin line source. It'll have some length here. I'll be able to get the length from the parameters in our diagram here. It'll have some length. It has some area, right, involving the length. It'll be the length multiplied by this differential distance here. That's the moving area. We multiply by u naught, we get the source strength. So I just realized something. Is this a small source? God, I can't believe I've never worried about this before. Oh, we're saved. Wow, this is subtle. Hold on, I need to make a note of this. Okay, so we know we're off here at some angle, right? We know how this is going to contribute to this. If it's a small source, we know how this is going to contribute to the sound field, right? We in fact found it. We found this with this radiation. Oh, all right, sorry, I'm wrong. It doesn't have to be a small source. We know the solution. We know the exact solution for a pulsating rod. I'm really confused. I'm sorry about this. This happens every Monday. I don't know if you've noticed. To me, every Monday this happens. There's a pattern there. I'm going to have to look into this. Maybe we might be able to fix it up right now. Let's see if we can fix it up. We know, yes, we can fix it. So you guys can speak up, you know, when I'm struggling like this, you can speak up. We know the far field for any wavelength. We didn't make any assumption about the size of the wavelength compared to the source. We did not make the small source approximation here. Right? Okay, you can look back, I'm sure of that. Now, we found it, you have to think about this. We found it as a function of angle this way, right? Remember, this is the in-fired, so-called in-fired situation. Here's the perpendicular, okay? Now, what we needed here it is, all of our contributions here are not going to involve, we called this theta before, and I call it theta prime now. For us, theta prime is equal to 0. So we take our solution here, which holds for any wavelength, and you can see that. It's any Ka value. You can clearly see it right here. All I had to do was look here. Remember the sine of V over V, where V is equal to this? Yeah. This, you know, Ka is not necessarily a small source. Ka doesn't have to be small. This is exact in the far field. So I've relabeled the theta as theta prime because we already have a theta here. But our theta prime is going to be 0. So what's the sine of 0 over 0, or the sine of V over V in the limit as V goes to 0? It's just 1, as we discussed. So we get this. This is just 1. We get a nice result. What's the source strength? It's the area. We're going to call this integration variable x right here. We've got a dx. So the moving area is the length. Okay, and I can get the length from the trigonometry here. The length is just going to be 2 times a times the sine of theta, because our excuse me. It's going to be, the theta's here. You can see it from here in this 3D drawing. It's going to be the sine of phi, right? So we can write down our source strength, substitute that into here, and form an integral. Okay. Now, when we do that, because we're going to the far field, this r prime will approximately be r, right? We're going to be way out here. So in the denominator, the difference between r and r prime, all our values of r prime, is going to be negligible. Okay? But we cannot make that assumption in the exponential because that involves the wavelength that is not necessarily small. So we have to we do our usual thing here. Remember the path difference when you're far away here. The path difference, this point is far away compared to the size of the source. We can relate r prime to r. They become approximately parallel. They become parallel in the limit as this goes infinitely far away. This solid line and this dashed line become parallel. It's very easy to calculate the path difference. It's just x, which is right here, this distance, times the sine of theta. So we've been through this all before several times. In the exponential, we have to do this. And now x is a times the cosine of theta. So here is our differential pressure contribution. The contribution to the pressure from this elemental source here. Okay, from this source right here. We need to integrate over all these. And you can see it's starting to look really ugly. Because what are we integrating over here? I haven't beaten it down to one variable yet. What are we going to integrate over here? Well, it turns out what you want to do here, and you wouldn't know until you beat on this. We want to go to phi as our integration variable, not x, it turns out. You'll see why tomorrow. We want to integrate phi over all possible phi values here. Okay? So what that means is phi equals 0 to phi is equal to pi. And you can see that this looks like it's going to be there's phi. It's sitting up there, and it's sitting right here. And we still have to convert the dx to phi. Okay, so it looks like this is an impossible integral, but a special function comes to our rescue. And special mathematical functions, that's what they're usually called in physics. And we'll see about that tomorrow.
Wouldn't it have to be 0 to 2 pi? All the way around this circle.
See, for each